All right, I've been warning you that this class is about to get more difficult, and here's the moment where it becomes more difficult. So here's definitely the most difficult problem we've encountered so far, and one of the most difficult things we'll do all semester. So I know this is going to be a little bit challenging to follow, but if you can get through this material, this 2D kinematics material, you can handle anything in this course. So stick with it. What we're going to do now is projectile motion in 2D. So projectile motion means that's the type of motion that happens when you throw an object through the air and it is accelerated by gravity alone. So once I let go of this pen, the only acceleration on it is the downward acceleration from gravity. There's no other acceleration happening horizontally. And this is kind of a classic physics problem. In fact, a lot of this stuff was developed in the first place to study motion of projectiles because of war and people shooting cannonballs and stuff. They wanted to figure out how far a projectile, a cannonball, would travel, or a bullet. But you can apply this to all sorts of situations, and the one we're going to tackle right now is just imagine that you throw a ball, and for simplicity, we'll assume the ball starts out at ground level. I know when you throw an object, it's actually starting from higher than ground level, maybe 2 meters, a meter or two above ground level, but we'll make it easy. Say it starts from zero height. You throw it with a speed of 30 meters per second at some angle 40 degrees above the ground. And we're going to answer all these questions. We're going to describe this motion. We'll find its maximum height, we'll find how far it goes, we'll find the time that it takes to get to the maximum height and how long it takes to land. We'll find the ball's final velocity. So to do all this stuff, we're going to use our procedure that we learned for 1D kinematics. Remember, we first identify that it's a kinematics problem. So far, everything in this class is kinematics problems. Later on, we'll learn non-kinematics problems. Then we identify our known quantities, identify our unknown quantities that we're solving for, choose the right equations to use, and solve those equations. The difference now is that we're in 2D, so we actually have 2 sets of kinematic equations. We have those 4 kinematic equations for the x component and the y component. So the same 4 equations, just written twice. These describe the horizontal motion of the projectile, of this ball, and these describe the vertical motion of the projectile. Remember, horizontal and vertical motion are independent of one another. They don't affect the other. Now the very first thing I want to do before we even start answering any of these questions is I just want to sketch what this motion looks like and draw some general conclusions about it. So let's say you launch this ball from ground level, you throw it from ground level. It's going to travel in a parabolic arc. You can take my word for it for now that it's a parabola. And let me draw this ball at a few different instances along the path. And we'll think about, I didn't mean for the ball to get bigger. Okay, we'll think about its velocity at each of these instances. So when you first throw it, it has a velocity vector like so. This vector has a magnitude of 30 meters per second, and it has an angle. I didn't draw this to scale, sorry. It's a little bit bigger than 40 degrees, but I did the best I could in my drawing. So it has a magnitude of 30 meters per second and an angle of 40 degrees above the ground, above the horizontal, above the x-axis. So this initial velocity vector has an x component and a y component. Right? It's got a y component and an x component. So we'll call that Vx initial, I for initial, and we'll call that Vy initial. And now as this thing travels on its path, the velocity vector always points tangent to that path, or parallel to that path. And now something interesting happens with this velocity vector. In the horizontal direction, I didn't draw this very well. Let me change that sketch a little bit. There, that's better. In the horizontal direction, there's no gravity acting. There's no acceleration in the horizontal direction. And remember that acceleration means change in velocity. So if there's zero acceleration horizontally, that means there's zero change in horizontal velocity. So at every instant, this Vx is the same value. It's the same value as it was at the beginning. In the vertical direction, though, you have acceleration from gravity pulling you down at a rate of 9.8 meters per second squared. So if this velocity was initially pointing up and acceleration is pointing down, it's going to get smaller. And it's going to keep getting smaller until you reach the peak of that motion. And at this peak, at this maximum height, Vy is 0. And Vx is still that initial value, and the overall velocity is just Vx in the x direction, the I hat direction. So what happens at the maximum height is that the y velocity momentarily goes to 0. You have gone up, and then at the very peak, that y velocity stops, and then it comes back down. And so for the rest of this motion, you still have this constant x component of velocity. It's the same value the whole time. And now y velocity is pointing downward. The object has started to fall down. And then by the time the ball is just about to hit the ground, its final velocity vector looks like that. And there's your Vx, which is still that same value it's been the whole time. And here's Vy final. There's V final at the very end. And we'll figure out what these these values are in part E of the problem. Okay, so keep in mind as we're doing these, this picture, you're launching the ball at an angle, so we're going to find the initial components of that velocity. But then in the horizontal direction, that x component stays the same the whole time because in projectile motion, there's no acceleration along x. Therefore, there's no change in x velocity. In the y direction, gravity is pulling you down, so that y motion is the same as if you just throw an object straight up and straight down. As far as the y direction is concerned, that's all that's happening. You start up, but gravity is pulling you down the whole time, so you reach a peak height and then start falling down. At that peak, the velocity is purely horizontal. Okay, let's start answering the questions. First thing we should do is turn that velocity vector, which is given to us in magnitude angle form, and write it in component form. So there's 40 degrees, 30 meters per second. That's our initial velocity vector in graphical and magnitude angle form. In component form, we use our trigonometry skills. That x component is adjacent to the angle, so it gets cosine. 30 meters per second, cosine 40 degrees. So I'm trying to remember about these significant figures. And that would give you 22.98 meters per second. The y component is opposite to the 40-degree angle. That gets the sine. $19.28. Speaking of significant figures, it's a good habit when you're doing intermediate calculations, not your final answer for the problem, but any intermediate calculations, to keep an extra digit or two. This helps prevent rounding error in your calculations. So my final answers for these should have 3 significant figures because that's the information that was given. I'm writing this with 4 so that I don't end up with rounding errors. All right, I'm going to put this information in a box because I'll need these for all the parts of this problem. So Vx initial equals 19.28 meters per second, and Vy initial is, sorry, that's backwards. 22.98 and 19.28. Okay, now we can start answering stuff. We'll follow our problem-solving procedure. So, part A, the question is how long does it take to reach the maximum height of that motion? So, let's go through our procedure. We identify that it's a kinematics problem. Sure it is. Now let's identify what we know. All right, well, we know Vx initial. I've got those values there, I don't need to write it down. We know Vy initial. We also know that at the maximum height, the y velocity is 0. So we'll say Vy final equals 0. Now remember, initial and final refer to the particular situation you're analyzing. So in parts A and B, my final is going to be at the maximum height. For parts C, D, and E, final will mean something different. Final will mean after the ball's landed on the ground. So keep in mind that my initial and final change depending on exactly what I'm trying to answer. But in part A, Vy final is 0 because at that peak of the motion, there's no y velocity. There's still x velocity, but not y. We know if we care to write this down, that Vx final at that peak height is that same value of Vx initial. It's still 22.98 meters per second. We know the acceleration in the x direction is 0. We know the acceleration in the y direction is minus 9.8 meters per second squared, because that's what the Earth's gravity always does. And we also know x initial is 0, y initial is 0. Okay, so we've got a bunch of information there. What do we want to find? Well, we're looking for the time. So we need to use the right equation for the job. And now we have a list of 8 equations to choose from. So you need to go through this list of 8 equations and see which, if any, are going to be useful. And maybe to save time, I'm just going to point out that I want to use this first equation from the y direction. None of these x equations are going to be helpful. They all contain too many unknowns and there's no way to solve them given the information we have. And in the y direction, they all have too many unknowns except for that first one. All right, so we know that Vy final is 0. So we'll replace that with 0, and then we can solve for time. T equals minus Vy initial divided by A y. And if we put in those values, negative 19.28 meters per second, negative 9.80 meters per second squared, we find that it takes 1.968 seconds to reach the top. There's some extra digits there for your possible intermediate calculations. And if I just want to express this as my final answer, I'll round it and say 1.97 seconds. All right, part A is done. We still got a lot more to go, so stick with me. B, what is the maximum height? Let's do the procedure. We know it's kinematics, and we know a bunch of stuff. Okay, what do we know? We know x initial, y initial, v x initial, vy initial, ax, ay. We also know vx final, because that's the same as vx initial. We know vy final, it's 0. And we just solve for the time. Again, keeping in mind that for part B, at the maximum height, this is the same final situation as in part A. So these final values, Vx final, Vy final, and the time refer to the same situation as in part A. Things will change in the rest of the problem, but that's what we mean by final for part B. We're at the peak of that motion. All right, so that's a nice long list of stuff we know. What are we looking for? We want the final height at the peak. That will give us the maximum height. So we need to consult the list of equations. Which one should we use? Well, none of the x equations do us any good, because y final is not in any of those. So don't even look at those. Let's go to the y equations. We need a y equation that involves y final, so that could be 2, 3, or 4. And it looks like any of those would work. 2, 3, or 4. I think we know all those values. So let's just pick the easiest one to use, and I think maybe equation 2 is the easiest one to use. If you want, you can use either of those. You might double check by trying those. But this is pretty simple because y initial is 0. We can cross that out. It starts from ground level. And we know Vy final is also 0. That y velocity is 0 at the peak. So we can cross two of those things out, and the equation is pretty simple. 1/2 Vy initial t. We know those values. We've got Vy initial over here. We solve for t in part A. And remember, I kept an extra digit for t because I knew I would need to use it later to prevent rounding error. So use that unrounded version of t, 1.968. And when you plug those in, you get 19 meters, properly rounded. Okay, part C. How long is the ball in the air? So you throw that ball from ground level, soars through the air, hits the ground again. Our final situation has changed. Initial, ground level, final, ground level again. So what we did in A and B no longer applies. So don't use that value for time that we found in part A. Don't use that value for final height that we found in part B. Those no longer make sense for the rest of these questions. All right, procedure. It's kinematics, and here's what we know. Remember, it's a different set of information now because it's a different final situation. We still know the same initial things. X initial, Y initial, those are both 0 because it starts the origin. We know V X initial, we know V Y initial. We know AX, which is 0. We know AY, minus 9.8. And we also know Y final. Y final is 0. The ball has hit the ground. Okay, so that's our list of information now. And what are we trying to find? The time. So let's use a good equation. Now again, I'll save you some time. I won't talk through every one of these, but there's only one possibility that's going to work, and that is this one, the third Y equation. If you don't believe me, this is a good exercise the first time you learn this. Look at that list, go through each equation, see what's in it, see what's not in it, see which ones are solvable for t. The only one that you could possibly solve for t is this third Y equation. And by the way, I know that sounds like it takes a long time, and certainly when you're learning this at first, it does take a long time. Once you have more experience, you just kind of know which equation is probably going to work for a situation. But certainly at the beginning, you do kind of need to go through this list and just check off which ones have the quantities you need. All right, well, I claim that this one's going to work. And let's solve it. Y final and Y initial are both 0. The ball starts at ground level and ends at ground level. So fortunately, that makes solving this equation a lot easier. Later on, we're going to do an example where it starts and ends at different heights, and that's when you have to use the quadratic formula. But we don't have to use the quadratic formula here. We can just algebra our way out of it. So follow along with me as I do a little bit of algebra to solve for t. I move this term over to the left-hand side. Now I'm going to cancel 1 power of t. And solve for t. So Vy initial, 19.28 meters per second, keeping that extra digit for accuracy. And that AY is negative 9.8 meters per second squared. You can assume for this number has more precision than I wrote. You can assume that there's more digits here that I didn't write. So we're not limited by the significant figures in that value of G. And that gives 3.935 seconds unrounded, because I'm going to need to use this again. Rounding, so I can give the final answer for part C, 3.94. All right, we're more than halfway there. I know this is a big problem. We're getting through it. Part D. I shouldn't have erased that first line. How far does the ball travel? Meaning, what's the horizontal distance it goes? This question is slightly ambiguous. A super complicated question would be, what is the path length that the ball travels? What's the length of arc? That's beyond what we do in Physics 6. So you can assume that when it asks, how far does the ball travel, it just means, what's the horizontal distance that you've thrown it? So again, our initial situation is the throw, and the final situation is the landing. We know it's kinematics, and we know a bunch of quantities: x initial, y initial, v x initial, vy initial, ax, ay, y final, and the time, because we just got the time from part C. It's the same time from part C. Unknown, the thing we're trying to find, is x final. How far does the ball travel? X final is what we want. So we need to choose the right equation to use. Since we're looking for x final, that means none of these y equations do us any good. We don't need to look at those. We just need to look at the x equations. And first one doesn't help, but any of these three will work. So let's do the third one. You can double check this by trying one of the other two equations, and you should get the same result. Yeah. Actually, the fourth equation won't work. The fourth equation will give you 0 equals 0, and you won't be able to solve anything. So either the second or third equation will work. All right, so we don't even have to do any algebra. It's already in the right form, so just plug in the numbers. X initial 0, the x initial 22.98 meters per second. That time was 3.935 seconds with my extra digit, and there is no acceleration in the x direction, that term is 0. So the ball travels 90.4 meters. By the way, notice that this kind of complicated looking equation simply turned into distance equals speed times time. That equation that you learned, I don't know, a long time ago in algebra or something, distance is speed times time, is one of the kinematic equations that's true when there's 0 acceleration. Okay, we've done part D. Only one question left. What is the ball's velocity as it lands? So remember, when we say as it lands, it doesn't mean after it hits the ground and stops or rolls away or whatever. It means the split second, that instant right before the ball strikes the ground. And when I say velocity, I mean vector. So we'll write this answer in vector form. We'll do it in component form, and we'll also figure out the magnitude and angle. Let's do it. It's kinematics. Here's what we know. Whole bunch of stuff. X initial, Y initial, Vx initial, Vy initial, Ax, Ay, Y final, T, and X final. We found T in part C. We found X final in part D. What's our unknown? What are we trying to find? Well, we're actually trying to find two things. We're trying to find Vx final and Vy final. But, well, really, Vx final isn't so unknown after all. All along we've been saying Vx final is the same thing as Vx initial. So let's, we'll show that Vx final is the same as Vx initial, and we'll solve for Vy final. So to show that Vx final is the same, we'll use that first kinematic equation for x. And to find Vy final, well, it looks like we can use the same equation for y. Vy final is Vy initial plus Ayt. So let's put in some values here. Vx final equals Vx initial plus 0, because Ax is 0. So we've just proven that Vx is constant the whole time. So 22.98 meters per second. If we were saying that's our final result, then we could round it to 23.0. And for y, it is 19.28 plus negative 9.8 times that time we found in part D, or part C. 3.935 seconds, which gives you yeah, negative 19.28 meters per second. We're rounding negative 19.3. Now check this out. That final y velocity is the same magnitude as the initial y velocity. It's just pointing down instead of up. So this motion, this projectile motion, is nice and symmetrical. The horizontal velocity stays the same the whole time, and the vertical velocity ends up the same magnitude, just pointing down instead of up by the time the ball lands. So if we write our v final in component form, it's 23, negative 19.3 meters per second. If we write v final in magnitude angle form, then the magnitude v final is given by the Pythagorean theorem. When you plug in these numbers, guess what? It gives you 30 meters per second, which is the speed that we started with. Again, this motion is symmetrical. It lands with the same speed. It doesn't land with the same angle though, but it lands with a related angle. So that final velocity vector, 23, negative 19.3, looks like this. Theta is inverse tangent, opposite over adjacent. Guess what? That gives you 40 degrees, and that 40-degree angle is below the x-axis. So we launched at 40 degrees above the horizontal, and then when the ball lands, it has the same speed and the same angle, except the angle is tilted downward, below the horizontal this time. All right, so that's a lot of information. That's a lot of problem solving. This example involves everything we've learned so far this semester. And that's kind of how physics works. Our problems keep building on one another, and they will use all the tools that you learn along the way. So by even by the midterm, we'll be doing problems that involve maybe 3 or 4 techniques, all within one problem. So they all build, and physics is cumulative like that. All right, if you can handle this, you can handle anything in this course. Good luck.